Okay, in the previous video, we were introduced to the ideal gas law. Now, in this video, we're going to go through the basics of how the law was developed. So, over the centuries, gases were studied and separate laws were formulated governing the general behavior of gases. At some point in the 19th century, all of these laws were combined into one overarching general law called the ideal gas law. But before we get started, let's go through the meaning of the ideal gas law again. It's really important that we understand exactly what the ideal gas law means and how it works. So, okay, you can put the ideal gas law into different forms, but the most common form is PV is equal to nRT. Okay, so this law or this equation can be applied to any substance whatsoever that's in the gas phase. Remember, in general, any substance under certain conditions of temperature and pressure is able to exist in the solid, liquid, or gas phase. Even metals can be vaporized at high enough temperatures and combined with low enough pressures. However, the ideal gas law, the fundamental ideal gas law, is in reference to a gas that exhibits what's called ideal behavior, ideal gas behavior. A perfectly ideal gas will follow this equation exactly. And the more a gas deviates from ideal behavior, then the less precisely the gas will follow this equation. We'll talk more about the meaning of what exactly ideal behavior of a gas means. No gas is perfectly ideal, but you can think about, for the moment, the meaning of ideal in that the further a gas is away from the point of condensing, then the more ideal its behavior. For example, a substance in the gas phase is called a vapor if that gas is close to the point of condensing, like water vapor, for example. But again, because any substance can exist in all three phases, you could have something like oxygen gas, which at normal conditions isn't close to the point of condensing, so it's exhibiting ideal behavior. But if you change the temperature and pressure to where you have oxygen gas that's still a gas but close to condensing, then you would call it a vapor. Okay, and so if it's deemed necessary to take into account deviations of a gas from ideality, then modifiers are applied to this general equation, to the general ideal gas law, which we'll talk about at the end of the chapter. But right now, we're just going to consider substances in the gas phase in which the deviations from ideal behavior are negligible, and thus the fundamental equation, PV is equal to nRT, can model the behavior of the gas with acceptable precision. Okay, so how does this equation work? The idea is you'll be applying this equation to a gas body. In any scenario, you could have a solid, liquid, or gas body. But specifying a certain gas body is a little more ambiguous than specifying a solid or liquid body. So a gas body is a volume of gas enclosed by an imaginary surface. Most commonly, for the majority of gas bodies that we deal with, this imaginary surface is going to coincide with the inner walls of a solid container, like this home air compressor, for example. The compressor is on top, the tank below holds the compressed air. The imaginary surface holding the compressed air would line up with the inner walls of the tank. Same idea with the propane gas in this tank. Same idea with these pressure vessels here, these gas pressure vessels here, or with these pressure vessels here. However, you could have a gas body like all of Earth's atmosphere. In this case, the imaginary surface enclosing the gas body would be Earth's surface and the surface of the oceans on one side, and then the boundary at the edge of space on the other side. Or the point where there's no more gas molecules. right? Because space is a vacuum. Okay, now, but from all of these previous examples with these tanks, there's two differences of those examples from the Earth's atmosphere example of the imaginary boundary enclosing a gas body. So first, one of the boundaries of Earth's atmosphere is unable to push back on the gas and create a pressure, right? At the edge of space. At the edge of space, the atmospheric pressure must be zero because there's nothing to push back on the gas. Now, the second difference is that for the boundaries at Earth's surface, which push back on the gravitational pull of the atmosphere towards Earth's center to create a hydrostatic gas pressure, one of those boundaries is a liquid boundary, Earth's oceans and Earth's lakes. So a boundary of a gas body could be a solid or a liquid or even a vacuum. But we'll see in a second that a boundary could also be another gas or even the same gas. But note that only a solid, liquid, or gas boundary will be able to push back and create a non-zero pressure. And so, like, okay, a boundary enclosing a gas body could be another gas if we think about the atmosphere surrounding this industrial plant. So this is at some latitude and longitude location, right? Some elevation relative to sea level. Well, you could consider enclosing the atmosphere around this industrial plant with a boundary that aligns with Earth's surface below, as well as, say, 100 feet up from Earth's surface. You would put a boundary here, a horizontal boundary, and then say that there's some vertical boundaries all along the property line that extend 100 feet up. Right? So in this case, you do have, there's gas boundaries. And these gas boundaries are able to push back. The atmosphere gas from above can push down. This atmosphere gas can push from the sides. But you also want to note how the boundary surrounding a gas body is going to have specific characteristics applied to it. You have to be specific about exactly how the boundary of a gas is defined. So notice here, for the atmosphere around this industrial plant, I said that the boundary aligns with Earth's surface below, okay? Then there's another horizontal boundary 100 feet above the surface. And then on the sides, there are vertical boundaries that align with the property line that extend 100 feet up. So I'm giving a distance of 100 feet up and along the property line. And so in that case, I'm implying that the gas boundaries above and on the sides are fixed. The boundary aligning with Earth's surface must be fixed because Earth's surface doesn't move. But the boundaries aligning with Earth's atmosphere are more ambiguous, right? These boundaries aren't going to necessarily be fixed in space depending on how they're defined. By saying that the top boundary is 100 feet up and the side boundaries are aligned with the property line and then extend 100 feet up, I'm implying that these boundary, their locations in space are fixed. But I could have defined these boundaries another way. I could have said that, so at time t is equal to 0, at the starting point, the boundaries are defined exactly like they were defined here, the lower boundary with Earth's surface, the side boundaries along the property line, etc. But then instead, the statement could have been made that at time t is equal to 0, this volume is going to enclose a certain number of air molecules, a certain number of moles of air molecules. And the boundary is such that the boundary is going to always follow that same original number of air molecules. Well, in that case, the location of the side boundaries and the boundary above can change. It's going to stretch or shrink and conform to that same number of moles of air molecules. Or for the case of a balloon like this, if you said that the gas boundary is the entire interior surface of this balloon, as well as the cross-sectional area, let's say you're not considering once you tied the balloon closed, you're looking at it at this state here with the pump. So the gas that's being enclosed is the entire interior surface of the balloon, as well as the cross-sectional area of the inlet. Well, then in that case, the boundary can expand or contract, right? But then also based on that definition of the gas boundary, you're allowing for air molecules to enter or leave the gas body. You see? Okay, so that's a gas body. That's how a gas body is defined, with some imaginary boundary surrounding the body. And again, the idea is that the ideal gas equation is in reference to some gas body. And the way it works is this: the state of the gas body can change with time. Things can happen over time. Gas molecules could enter or leave. The boundary could expand or contract. The temperature could change. The pressure could change. Okay, but this equation is in reference to any given snapshot or moment in time. So like, for example, you could track a given gas body for an hour and take an image, a snapshot of the gas every minute. And in that case, you would be applying this equation separately for each of those 60 minutes. Okay, but however, right now, we're only considering cases of gas bodies for which at any given moment in time, at any snapshot, these parameters, so the pressure, the volume, the number of moles of gas molecules, the temperature, this is just a constant. At any given moment, these parameters are assumed to be uniform, spatially uniform, throughout the entire gas body. So we're assuming the pressure is uniform, the volume is uniform, the gas molecules are distributed uniformly, the temperature is uniform, spatially uniform. At any given moment, we're assuming that you can describe the entire gas body with a single pressure value P, a single volume value V, a single number of moles value N, and a single temperature T. Now, perhaps at another moment, the pressure, temperature, volume, or number of gas particles would be different. That's fine, but at any given moment, the entire gas body can be described by a single P, V, T, and N. Now, it's not that the ideal gas law has no way of being applied to a gas body in which the pressure, volume, temperature, or the number of moles, or the way the gas particles are distributed, are not spatially uniform at a given moment. But that's an advanced topic that we're not considering in this chapter. Okay. However, if you think about it, though, for a lot of the cases in terms of the gas bodies we deal with on Earth, an assumption of constant parameters like this at a given moment is a very precise assumption. The compressed air in this tank, right, you could say at some moment has a single pressure, temperature, volume, well, the volume's fixed, and number of gas molecules. That's uniform throughout the entire volume. Same idea with this propane tank, and with these pressure vessels, and these pressure vessels. And even for the case of like Earth's atmosphere, which on the whole, taking Earth's atmosphere on the whole, it's not possible to ever have a single uniform pressure throughout, because at the edge of space, that the pressure must be zero, and then the closer you are to Earth's surface, the more weight of air is above you, meaning the pressure is increasing going towards Earth's surface. Well, for the case of the industrial plant, bounding off of a volume of atmospheric air in this region allows you to make a solid assumption that the air pressure at a given moment is some uniform constant value P. Or like here, for example, I believe this is a propane pipe system. There's propane gas in these pipes. Well, if you consider the entire volume of propane gas at a given moment throughout the entire pipe system, then the pressure is not going to be uniform. The pressure will be higher near the main compressor that's pushing the propane through the pipes, and lower further away from the compressor. But you could still consider making a boundary within the pipe somewhere like shown here. In this case, you could potentially make the assumption, I don't know the details of this system, but you could potentially make the assumption that the pressure and temperature are uniform values throughout this region, spatially uniform throughout this region at any given moment. Now, note how with the way the boundary is defined, the volume would never change from moment to moment, but perhaps N would change because you have gas molecules can pass through these boundaries. Okay, but now you want to keep in mind, though, that any assumption we make in engineering or science is never perfect. For example, if you've got gas in these tanks, well, you could say that the gas at the bottom of the tanks has an extra pressure on it due to the weight of gas above it, an extra hydrostatic pressure. And technically, that is true. Technically, if you're being perfectly precise, the gas in these tanks can't have a perfectly uniform pressure because the gas towards the bottom is going to have a little more hydrostatic pressure to the weight of gas above it. But a hydrostatic gas pressure for the case of a tank like this would be negligible. In most cases, there's plenty of enough precision overall to assume a constant pressure, and the same idea with temperature. Now, don't get too comfortable, though. As an engineer or designer, you need to be careful because, like perhaps, for example, on a hot, sunny day, then the surface of tanks like this could get very hot, right? Well, in that case, maybe there is a non-negligible temperature gradient in that gas that's inside the tank that's near the surface of the tank has a higher temperature than gas towards the center, to where it's no longer correct to assume a uniform temperature. Okay, and so now you can see how the ideal gas law works. The ideal gas law is just saying that at any moment in time, if you take a snapshot of a gas body, if it's the case that you're able to assume that the gas body is under some spatially uniform value of pressure, temperature, volume, and number of moles of gas particles at that moment, which in the majority of cases you are able to do this, then at any of those snapshots, this equation is going to hold. Now, if it's the case that the gas in the gas body is relatively close to the point of condensing, then the gas will exhibit non-negligible deviations from ideal gas behavior. In this case, you just need to apply modifiers to this equation that will result in a more precise model of the gas behavior or the gas properties. So that's it. That's how the ideal gas law works. Okay, so now we want to go through how the ideal gas law was developed. Again, over the centuries, gases were studied and separate laws were formulated governing the general behavior of gases. And at some point in the 19th century, all of these laws were combined together to create one overarching general law called the ideal gas law. Okay, now as we go through these laws, note how the gases that these scientists are studying are not vapors. They're gases like substances that exist as gases at normal atmospheric conditions. No gas is ever ideal, and again, we'll talk more about what ideality means later in the chapter, but the gases in these studies are relatively ideal in the sense that they're far removed from the point of condensing. Okay, let's start with Boyle's law. In the 17th century, Robert Boyle studied the behavior of gases systematically and quantitatively. In one series of studies, Boyle investigated the pressure-volume relationship of a gas sample. Typical data collected by Boyle are shown in the table below. Note that as the pressure P is increased at constant temperature, the volume V occupied by a given amount of gas decreases. Okay, so Boyle studied the behavior of gases by conducting tests at constant temperature and varying the pressure and the volume. So here they show an illustration of the types of tests Boyle was conducting. And so specifically, we want to think about this as these are constant temperature tests and constant amount of gas. So even the amount of gas doesn't change as the pressure and the volume are changed. So you've got this manometer tube here. It's an open-ended tube. So atmospheric pressure is applied to the gas as well. And here, so once this system here settles into equilibrium, you've got atmospheric pressure applied to the gas, and that's it, because there's no height of mercury being held up by the gas. So it's just atmospheric pressure. And then at the same time, there's a corresponding volume of the gas, which would be given by, you take this length times the cross-sectional area of the tube. But then also at the same time, once everything settles in, there would be some equilibrium temperature of the gas, which could be like room temperature, the temperature of the lab, or any temperature. Okay, now what's done next is you add mercury to the tube to where once you add some mercury and wait for the entire system to settle into a new equilibrium state, then what you'll have is a new pressure given by the atmospheric pressure plus this additional 760 millimeters mercury and a new volume of gas, which again, you just take this length times the cross-sectional area of the tube. But then at the same time, the way you want to think about this is, so whenever you're adding the mercury here to get to this state, potentially as you're adding the mercury, as the state is changing, maybe the temperature of the gas changes. It goes off from what it was in this state. But as long as once you get to this final state, or whatever this final state is, you make sure that the equilibrium temperature that the gas is settled into is the same that it was here. Then you're conducting a constant temperature test. It's just that the final temperature you settled into is the same from one state to the next, right? Once you record this new volume, this new pressure, it needs to be the case that at that moment, the equilibrium temperature is the same as it was here for you to consider it a constant temperature test. Okay, and then same idea here. They add more mercury, you get a new pressure, a new volume, and you're going to make sure the equilibrium temperature is the same as it was here and here. Okay, but then also note that you're not changing the amount of gas either in this process. The total number of moles of gas never changes. Okay, so you can think about how Boyle conducted tests like this, just varying the pressure and the volume at an array of different constant temperature values and with different gases. Right now, it says how so here's the data from a typical test that Boyle would have conducted, and what they're noting is that, so you compare the first data point with a pressure of 724 millimeters mercury and a volume of 1.5, an arbitrary unit. Yeah, they're just saying that you could, this 1.5, you could express the volume, you could just write whatever this length is, right? And that would be representative of the volume since the cross-sectional area isn't changing. So, 1.5 is, whatever this means, just some representation of the volume. You compare the 724 1.5 to the last data point with a pressure of 2250 and a volume of 0.58. Clearly, there is an inverse relationship between pressure and volume of a gas at constant temperature. As the pressure is increased, the volume occupied by the gas decreases. Conversely, if the applied pressure is decreased, the volume of the gas occupied increases. Yeah, so this makes intuitive sense, and the data backs up our intuition in that we see if as the pressure on the gas is increased, the volume decreases, and vice versa. You decrease the pressure, the volume increases. And then just note that for this test, this is going to be at some temperature, constant temperature T, and some constant amount of gas in. All right, but now it says that this relationship is now known as Boyle's law, which states that the pressure of a fixed amount of gas at a constant temperature is inversely proportional to the volume of the gas, right? The pressure of a fixed amount of gas, the amount of gas is constant, and the temperature is constant, is inversely proportional to the volume of the gas. Now, they've actually made an additional statement here that wasn't stated before. Yeah, so we looked at how it was the case that as pressure increased, volume decreases and vice versa. But, you could look at a relationship like this. So here's pressure and volume. Well, okay, here, as pressure decreases, volume increases and vice versa, right? But what they're saying is that what Boyle found was at some given temperature and amount of gas, there was a linear relationship, right? Inversely proportional, right? Boyle found this inversely proportional relationship between pressure and volume, no matter what the gas was, no matter what the constant temperature was, or no matter what the constant amount of gas was. And so that's what they're here. They just described the test setup. But what Boyle found was that, again, it's the pressure is, you can write inversely proportional. Like if pressure is inversely proportional to volume, then you can state that as the pressure is proportional to 1 divided by the volume. And for any proportionality like this, when you say two things are proportional, you can turn that into an equality by just saying, okay, this is equal to, and put some arbitrary constant times the value on the right-hand side times 1 over V. Okay, so again, what Boyle found, let's make sure we understand this. What Boyle found was, so he could take any gas, as long as it's a gas, we're thinking about gases that are far removed from the point of condensation. So you can imagine he's doing this with substances that exist as gases at normal conditions, right? Like oxygen gas, hydrogen gas, nitrogen gas, etc. So no matter what gas he chose, he would pick a gas, then pick some constant temperature to run tests at and some constant amount of gas. And then he would just vary the pressure. And as the pressure would vary, the whole system would settle into some new state with a new volume. He would record like 7 or 8 data points for that constant temperature, that gas, and that amount of gas, and analyze the relationship. And no matter what the gas was, no matter what the constant temperature was, no matter what the amount of gas was, he would get this inversely proportional relationship between pressure and volume. Now, what you want to note, though, is that the K1, the proportionality constant, is dependent on what gas he chose and what constant temperature he chose and what amount of gas he chose, right? Like you'd have all kinds of different lines relating. So this would be P and 1 over V. You'd have all kinds of different lines depending on whatever the temperature is and whatever the gas itself is, the type of gas it is, and whatever the number of moles of gas are. But in all cases, the relationship between P and 1 over V is linear. Okay, now what you can do is you can rearrange this equation by multiplying both sides by V, and you get P times V is equal to K1. And all this is saying is that, so again, you pick some gas and some amount of gas and some constant temperature, and you start just putting it in different states, adjusting the pressure, and there's going to be a new volume, right? Just getting a bunch of different PV data points. And what this is saying is that, so if we come here, if you come to like one state and you multiply the applied pressure times the volume, you're going to get a value. Then you go to another state and you multiply that pressure times the volume, and the value you get is going to be the same value that you got here. And then same here. Whatever you take this pressure times the volume, you're going to get some constant that's the same constant as here and the same constant as here. Again, this is for a given type of gas, a given amount of gas, and a given constant temperature. Okay, now it says the top diagram in the figure on the next page is a schematic representation of Boyle's law, and they actually start talking about the final ideal gas equation. I want to skip over this right now. We'll come back to this later. I don't want to go through this chart at the moment. To me, it makes it confusing. So let's just come here. It says the figure above shows two conventional ways of expressing Boyle's findings graphically. Figure 5.7a is a graph of the equation PV is equal to K1, So yeah, the actual relationship between pressure and volume, not the relationship between pressure and 1 over volume, is as shown here, right? So the linear relationship is between that pressure is proportional to 1 over volume. But if you actually translate this into what the relationship is between pressure and volume itself, then you get like a 1 over x type curve. F of x is equal to 1 over x, right? Like a rational function. You've got these like a horizontal and a vertical asymptote. Here, at all points along the curve, if you multiply the whatever the pressure is and the volume is, you're always going to get the same value, right? Take this pressure times this volume, you get a constant. Take this pressure times this volume, you get a constant. But then, of course, here there's a line, and that constant value you were getting is the slope of this line, the slope of the line that relates pressure and 1 over volume. And again, just keep in mind, all of this is for a certain type of gas, a certain amount of gas, and a certain temperature. Those three parameters don't change for Boyle's law, for the test that Boyle was conducting. The constant K1 is for some given type of gas, some given amount of that gas, and some given constant temperature. Okay, now here they just talk about the whole PV is equal to K1. What that means is that for any state, if you've got that same gas, same amount of gas, same temperature, you can put that system into any pressure volume state that you want. Just adjust the pressure, let it settle in, and you get a P1 and a V1. Change the pressure again, you get a P2 and a V2. Change the pressure again, you get a P2 or a P3 and a V3, right? Well, any of those, P1, V1 times V1 is going to be equal to P2 times V2, is going to be equal to P3 times V3 because they're all equal to that same constant. Okay, so that's Boyle's law. Now, next, let's look at Charles and Gay-Lussac's law. So Boyle's law depends on the temperature of the system remaining constant. But suppose the temperature changes. How does a change in temperature affect the volume and pressure of a gas? Okay, so yeah, now with tests from Jacques Charles and Joseph Gay-Lussac, they want to see what changes in temperature, how changes in temperature affect a gas. So let us first look at the effect of temperature on the volume of a gas. The earliest investigators of this relationship were French scientists Jacques Charles and Joseph Gay-Lussac. Their studies showed that at constant pressure, so what they're going to do here is, this is very similar to Boyle's tests, except now the pressure is going to be held constant and the temperature and volume are going to be adjusted. But then also what's also are constants similar to with Boyle's law are going to be the amount of gas is going to be held constant, and then the type of gas is obviously held constant, right? Whether it's nitrogen or oxygen gas, etc. So their studies showed that at constant pressure, the volume of a gas sample expands when heated and contracts when cooled. So here's just an illustration, a simple illustration of how a test like this would be performed. You've got your gas sample here, and you can add a certain height of mercury on top. So with the atmospheric pressure and that the column height of mercury doesn't change, so the pressure is constant, right? But also the amount of gas isn't changing, and obviously the type of gas isn't changing, but then you can adjust the temperature. So you let the whole system settle into equilibrium here, into this equilibrium state, and you've got some temperature that's settled in with the pressure is the same with the column of mercury and the atmospheric pressure, and you can record the volume based on this length here in the cross-sectional area of the tube. Okay, but then you change the temperature, you put some heat to this, or you cool it and whatnot. Here they've heated it, and you let the whole system settle into another equilibrium state to where you've got this gas is at some new temperature and some new volume with the same pressure, and then you record that temperature and that volume, and you just do this and get like 7 or 8 different data points. And what they're saying is that, in coordination with what our intuition would tell us, it was found that when the temperature was raised, the volume of the gas increased and vice versa. So the quantitative relations involved in changes in gas temperature and volume turn out to be remarkably consistent. For example, we observe an interesting phenomenon when we study the temperature-volume relationship at various pressures. At any given pressure, the plot of volume versus temperature yields a straight line. Okay, so that's really interesting. What they're saying is that, in this case, what Charles and Gay-Lussac found was that the relationship between the volume and the temperature, so they conducted tests on different gases. You've got the same amount of gas and you're holding the pressure constant, and the relationship between the volume and the temperature is always some straight line. It's not always the same straight line depending on what the constant pressure is and what the type of gas or the amount of gas is, but it's always a straight line relationship. Okay, but now, furthermore, it says that, so by extending the line to zero volume, we find the intercept on the temperature axis to be minus 273.15 degrees Celsius. At any other pressure, we obtain a different straight line for the volume temperature plot, but we get the same zero volume temperature intercept at minus 273.15 degrees Celsius. So this is really interesting. What they're saying is that if we come to this plot, you can imagine conducting a series of volume versus temperature tests on some gas sample. So you have the type of gas and the amount of gas is the same for all of these tests, right? But you're conducting a series of 4 tests varying the volume and the temperature, but at different constant pressure values. And so as we just talked about, what you're going to see is for each constant pressure, you're going to get this linear relationship between volume and temperature, this positively sloped line. Okay, but now what they're saying is, when analyzing this data, they decided to virtually extend these lines in the negative temperature direction. And by virtually extend, what they're saying is that at some point when the temperature gets too low, you can't actually conduct these tests because the gas is going to condense, right? So that's what they're indicating here with the dashed line, and that the gas would be condensed here. But with the solid line, these would be based on actual data points. And so what you would find is, for this specific gas sample, all of these lines, when virtually extended, are going to meet at a common point on the x-axis, so like an x-intercept, the intercept of the temperature axis, where the volume is equal to 0. With the temperature of this common point on the temperature axis corresponding to, if your temperature is in degrees Celsius, minus 273.15 degrees Celsius. And what you want to think about is that this is really interesting. It's interesting because if we think about a group of lines, they don't have to meet at a point. You could have, a line like this. They'll have to intersect if they're not parallel, but they absolutely do not have to meet at a point at all. Okay? Furthermore, if they do all meet at a point, that point does not have to be an x-intercept, an intercept of the horizontal axis. You could have something like this. Right? But then furthermore, it doesn't have to be the case that if you conducted a test like this with a different gas sample, perhaps the same type of gas, but with a different amount of gas, or just a different type of gas, it doesn't have to be the case that the volume versus temperature lines all meet at the same common point on the x-axis for that other gas sample, with that point on the x-axis being minus 273.15 degrees Celsius. But that's what they found. No matter what the gas sample, the type of gas and the amount of gas, if you do a series of tests like this at different constant pressures, a series of volume versus temperature tests, you're going to get this phenomena here, with the virtual extension of all of the constant pressure lines meeting on the horizontal axis at a volume of 0 at a temperature of minus 273.15 degrees Celsius. Okay, so in 1848, Lord Kelvin realized the significance of this phenomena. He identified this minus 273.15 degrees Celsius temperature as absolute 0, theoretically the lowest attainable temperature. then he set up an absolute temperature scale, now called the Kelvin temperature scale, with absolute zero as the starting point. Yeah, so Lord Kelvin looked at plots like this for different gases and said that, well, it must be the case that if we think about the idea of what it would mean for a gas to have a volume of zero. So at the time, we're going to study later in this chapter the kinetic molecular theory of gases, and this is just how we relate temperature, the temperature of a substance, to the inherent motion of the molecules of that substance. So motion in terms of actual linear motion for the case of a gas and a liquid, as well as vibrational motion, which would be present for gas and liquid molecules or atoms as well, in addition to linear motion. But with a solid, you don't have linear motion, you have vibrational motion. So you can imagine Lord Kelvin was theorizing that it must be the case that if a gas is going to have a volume of zero, what that means is that there's no motion, no vibrational or linear motion whatsoever of the gas particles, which means, from a macroscopic perspective, that the total temperature of that gas is zero. So he said, okay, well, let's create a new temperature scale called the absolute temperature scale, where a temperature of zero on the absolute temperature scale is the lowest possible temperature that a substance can have in the universe. And he just set that 0 point equal to this minus 273.15 degrees Celsius. And then it notes that, so on the Kelvin scale, 1 Kelvin is equal in magnitude to 1 degree Celsius. So what that means is that a change in 1 degree Celsius is equivalent to a change in 1 Kelvin. The Kelvin scale, the Kelvin absolute temperature scale, is you're just taking the Celsius scale and shifting it to the left, minus 273.15. You're shifting the 0 point of the Celsius temperature scale to the left, minus 273.15. That's it. Now, also, you can note, you might hear about the Rankine temperature scale, which is just an absolute temperature scale that corresponds to degrees Fahrenheit. What the Kelvin scale is to degrees Celsius is what the Rankine scale is to degrees Fahrenheit. So if you convert minus 273.15 degrees Celsius to degrees Fahrenheit, you get minus 459.67 degrees Fahrenheit. So with the Rankine scale, what you're doing is you're taking the Fahrenheit scale, taking the 0 point and shifting it to the left, minus 459.67. And then a change of 1 degree Fahrenheit is equivalent to a change of 1 Rankine. Okay, great. So back to the volume versus temperature analysis with this linear relationship between volume and temperature at constant pressure and constant type and amount of gas. What we're saying is that the volume is proportional to the temperature. So we can change this proportionality to an equality by just adding an arbitrary constant here. So this is K sub 2. So you get that volume is equal to some constant given by the slope of the line times temperature. Or you can say that volume divided by temperature is equal to a constant. And once again, let's just keep in mind that this K2 is, you're going to have a different K2 depending on the constant pressure and the type of gas and the amount of gas. And then here, when you rearrange an equation with all variables on one side and a constant on the other side, then what you're saying is that for some type of gas and some amount of that gas and some constant pressure value, so for some K2, then you can vary the volume and the temperature to whatever volume and temperature, as long as the gas stays a good bit away from the point of condensing. And no matter what, when you divide that volume by that temperature, you're going to get this constant. So what they're saying here is you look at that as it's, like V1 divided by T1 is equal to V2 divided by T2 is equal to V3 divided by T3 is equal to V4 divided by T4. Just take any volume divided by temperature, you're going to get that same constant. Okay, and so this is known as Charles and Gay-Lussac's law, or simply Charles's law, which states that the volume of a fixed amount of gas maintained at constant pressure is directly proportional to the absolute temperature of the gas. Okay, now you might notice how it it states Charles's law with respect to the temperature being the absolute temperature, right? It states that the volume of a fixed amount of gas maintained at constant pressure is directly proportional to the absolute temperature of the gas. Okay, so does Charles's law only work then with like Kelvin or Rankine? Well, obviously not, because I mean, look, the main tests themselves were conducted with degrees Celsius, right? But going forward in chemistry, really all throughout the physical sciences, now that we have these absolute temperature scales, we're going to want to apply science with the absolute temperature scale, right? The absolute temperature scale is more reflective of physical reality, right? With degrees Celsius, we've got these negative values relative to some arbitrary 0 point, which can be a problem. If we're trying to analyze something with Charles's law, with degrees Celsius, and so we're inputting some negative temperatures and we're getting out some negative volumes. What do negative volumes mean, right? So that's why you're going to see as we progress forward in this course, and really in any of the physical sciences, any kind of physical laws, properties, etc., are going to be based on absolute temperature scales. The Celsius scale and the Fahrenheit scale are just these human inventions that are convenient for us to compare a temperature to the freezing point of water or the boiling point of water. It just makes intuitive sense to us in our daily lives. But from a physical reality standpoint, we want to be working with something like the absolute temperature scale. Okay, now it says that another form of Charles's law shows that at constant amount of gas and volume, the pressure of a gas is proportional to temperature. So pressure is proportional to temperature. If the gas, you have a gas sample or the same type of gas, the same amount of gas, and the volume is held constant, and you're varying the pressure and temperature, then there's going to be a linear relationship between pressure and temperature with a constant of proportionality K3. So the pressure versus temperature relationship, depending on the gas sample, you'll have a certain line. Positively sloped line. Now, note that here, this is just another form of Charles's law. This relation between pressure and temperature is rooted in the experiments of Charles's law. All you're doing is taking this data and mathematically rearranging it to get another relationship between pressure and temperature. Okay, now you can divide both sides by T and get that pressure divided by temperature is a constant. So for some gas sample, if you're holding the volume constant, then you can vary the state in terms of the pressure and temperature, and no matter what state, if you take the pressure and divide it by the temperature, you're going to always get the same value. P1 divided by T1 is equal to P2 divided by T2 is equal to P3 divided by T3, etc. Okay, now, next we want to look at Avogadro's law. So the work of the Italian scientist Amedeo Avogadro complemented the studies of Boyle, Charles, and Gay-Lussac. In 1811, he published a hypothesis stating that at the same temperature and pressure, equal volumes of different gases contain the same number of molecules, or atoms if the gas is monoatomic. Thus, it follows that the volume of any given gas must be proportional to the number of moles of molecules present. So V must be proportional to N, or V is equal to a constant times N. Okay, so what are they saying here? Well, so Amedeo Avogadro published a hypothesis. He theorized that you could have an array of different gases, different types of gases, 7, 8, 9, however many different gases. But we're assuming all of those gases are far removed from the point of condensing. And if all of those gases have the same volume and are at the same temperature and pressure, then Avogadro hypothesized that it must be the case that all of those gases have the same number of gas particles, the same number of moles of gas particles. So it doesn't matter what the gas is. You could have one gas could be a monoatomic a noble gas, and another gas could be some long hydrocarbon type gas with big molecules. It doesn't matter what type of gas it is. If you have separate gases that are have the same volume and are at the same pressure and temperature, then both gases must contain the same number of molecules. And this is kind of weird to think about at first, because we can imagine that. So let's say we've got these 6 vials here. They're equivalent vials, and we're going to fill each of these vials with a different type of gas. And what we do is we just arbitrarily pump some gas in. We don't care about how much gas is pumped in. We just put some arbitrary amounts in each and then close the valve. Well, okay, so they're all at the same volume, and you would think that we might be able to just come to each and dial in the temperatures and pressures to where they all had the same temperature and pressure. And so if that's the case, then that means that they all must have the same number of gas particles. But how does that make sense? We just arbitrarily pumped in different amounts of gases in each. Well, the way you want to think about this is, so yes, the volumes are all the same. That's true. But when it comes to dialing in the temperature and pressure, I mean, yeah, you could dial in the same temperature on all of these, so you'll have the same temperature and volume, but the corresponding pressure is going to follow suit, right? Like you can't, once you pick a temperature, you're fixing the pressure. If you can't adjust the volume, or vice versa. If the volume is fixed, then once you pick a pressure, you're going to fix the temperature. So you won't be able to dial in the same temperature and pressure on all of these. The only way you could get those temperatures and pressures the same is by releasing some gas or adding in some gas. And if you did that, and then you dialed in the same temperature and pressure for all of these, then the theory is that, well, okay, you must have the same number of gas particles in each vial. Okay, so now the textbook isn't going to go into data that experimentally validates this hypothesis or like a whole proof of it. We know that Avogadro, this is the same Avogadro that's responsible for Avogadro's number, which also relates to counts of atomic-sized particles, right, in a substance. And so the proof of this hypothesis is mixed in with the whole proof of Avogadro's number, how you calculate Avogadro's number, etc. So that's all beyond the scope of this video. But assuming that this hypothesis is true, then we have Avogadro's law. So we'll have Boyle's law, Charles's law, and Avogadro's law. So assuming this hypothesis is true, then it follows that the volume of any given gas must be proportional to the number of moles of molecules present in the gas. So what Avogadro's law is saying is that if the type of gas is fixed, not the amount of the gas, because here we're actually relating to N, but the type of the gas is fixed, and also the pressure and the temperature is fixed, then if you would look at the relation between the volume of the gas and the number of molecules in the gas, you're going to get some linear relationship with different lines if you adjust what the constant temperature is or the constant pressure is or the type of gas. A positively sloped linear relationship, right? You increase N, you increase volume, and vice versa. So that's Avogadro's law, which states that at constant pressure and temperature, the volume of a gas is directly proportional to the number of moles of the gas present. So, okay, now we've gone through all of the foundational gas laws, all of the foundational developments of the properties of gases that were eventually all brought together, all combined together to form the ideal gas law. So now, next here, they talk about how Avogadro's law allows us to do stoichiometry on chemical reactions involving gases from another perspective, a volumetric perspective, but we'll come back to this later in a future video. Okay, so, but now next is, so we're going to bring, we have Boyle's law, Charles's law, and Avogadro's law. Those are the three gas laws we just went through. We can now bring all of these together, combine these together to create a single gas law that simultaneously relates volume, pressure, temperature, and number of gas molecules or particles. Okay, but now, how are these combined together? I always found this a little bit confusing because we could consider writing each of these equations as an equality with their own arbitrary constant, and then combining the equations together to create one overall equation. And that's in essence what they do here to arrive at the final combined ideal gas law. But what I always found confusing was that how are we able to assume that the different equations, that the different laws are allowed to be combined? We know that these laws are with respect to different conditions, right? This is a constant N and T condition. This is a constant N and P condition. By setting the equation for Boyle's law and Charles's law equal to each other, for example, it's like we're implying that a process is taking place in which the pressure, temperature, and volume all change. But Boyle's law doesn't apply when the temperature changes, and Charles's law doesn't apply when the pressure changes. Well, okay, I'm currently trying to find an official clear proof of how this works, of why precisely you're able to combine these. And when I do, I'll post a separate video. But I can give you an unofficial sense of this. So, okay, let me clear some space here. So let's say we've got some gas X. The type of gas is fixed. And this gas at a moment in time, at some snapshot, has a pressure P1, volume V1, temperature T1, and number of gas particles N1. This is state A. Okay, now let's imagine that this gas goes through a change of state at constant N and T, which would mean that its state would change to P2, V2, and T1, N1, because temperature and number of moles don't change. Now, this would be governed by Boyle's law, so you've got V times P is equal to a constant, so you would have V1, P1 is equal to V2, P2, right? Now, let's say that this gas here then goes through a change of state at constant N and P. So the final state in this case would be just P2 because P doesn't change, V3, T2, and N1. Okay, now this change would be governed by Charles's law, which is going to state that V divided by T is a constant, so V2 divided by T1 is equal to V3 divided by T2. Okay, now let's say that this gas changes its state at constant pressure and temperature. So the result is P2, V4, T2, and N2. This is governed by Avogadro's law, to where V divided by N is a constant. So V3 divided by N1 is equal to V4 divided by N2. Okay, now we'll say that this final state is state B. And what we want to do is we want to relate state A to state B. We want to think about, okay, this gas X went from state A to state B, which we know in the process, to get to state B, the pressure changed, the volume changed, the temperature changed, and the number of moles of gas particles changed. Okay, so to do this, let's start with this equation here and solve for V4. So V4 is equal to V3 N2 over N1. Now let's if we solve for V3 here, we would get V3 is equal to V2 T2 over T1, and we can substitute V3 in here. So V2 T2 into, and then T1 N1. Okay, now we can, if we solve for V2 here, we get V2 is equal to V1 P1 over P2, and we can substitute V2 here. So you've got V1 P1 T2 N2 over, and then that would be P2 T1 N1. Okay, now, if we just focus on, we have V4 is equal to this. What we can do is bring all of the V1s, P1s, the one subscripts to one side and everything else on the other side, and we get P1 V1 over T1 N1 is equal to P2 V4 over T2 N2. But, so this P1 V1 over T1 N1, that's state A. Right? And then P2 V4 T2 N2 is state B. And there you go. You see, this isn't an official proof, but this should give you a sense of how you are able to, if you have a gas that changes state with a change of pressure, temperature, volume, and number of gas molecules, you are able to combine these laws together, to set these laws equal to one another and combine the constants. So, okay. So that's what they do. If you combine these three laws, combine the constants, what you end up with is the ideal gas law, that PV is equal to nRT. All the constants get combined into there's just one constant here. And so there you go. This equation here for any gas whatsoever, assuming that the gas is far enough away from the point of condensing to where the deviations of the gas from non-ideal behavior are negligible, for any type of gas whatsoever, you have some gas body. If you take a snapshot of that gas at a moment in time, then if you're able to assume that there's, throughout the volume of the gas, there's one uniform pressure, one uniform volume, one uniform temperature, and a uniformly distributed number of particles of gas in, which in most cases you will be able to make the assumption of uniform properties, then this equation will always hold, no matter what state the gas is in, no matter what the pressure is, the volume is, the temperature is, etc. Now, what would make this equation even more useful is if we could solve for R, solve for what's called the gas constant, also known as the universal gas constant. It's universal because, again, this equation holds for any gas in any circumstance whatsoever. So this constant is just this one single universal value. And it would make this equation even more useful if we had R, because then we could be presented with a gas in some state at some snapshot in time. And then if we only know some of the information about the gas, if we only know its temperature and volume and number of moles, but not the pressure, then we could solve for the pressure. Or if we only knew the pressure, the volume, and the temperature, we could solve for the number of moles, right? Now, but you want to note, though, that I'm saying that solving for R would make this equation more useful. So it's not that this equation is useless if we don't have R. No. Because one way of using this equation is if you're comparing one state of a gas to another state. So you've got some gas X, the type of gas doesn't change, okay, but you've got one snapshot in time, we'll call that state A, and you've got another snapshot in time of that same gas, we'll call that state B, okay, but now going from state A to state B, you could have any kind of change in the gas in terms of the pressure could change, the volume could change, the number of moles could change, the temperature could change. All four of those could change potentially. Or maybe only two of those four change and the other two are constant. No matter what the scenario, no matter what the difference between the two states of the gas, the state A and state B of the gas, you can compare those two states with the ideal gas law easily. And the way you do this is really important to understand how to use the ideal gas law. There's really two ways you use the ideal gas law to analyze a gas. For the case, again, where you're comparing two separate states, two separate snapshots, all you're going to do is, again, this is completely universal. As long as the deviation of the gas from the ideal behavior is negligible, you determine that the deviation from ideal behavior is negligible, then this equation applies for all gases in all circumstances. So what you would do is, if looking at a gas, comparing a gas between two separate snapshots, the same gas between two separate snapshots, you're going to analyze, okay, going from state A to state B, what's constant? Or perhaps nothing is constant. And then you're going to come to this equation and you're going to rearrange the equation to where everything that's constant is on one side and everything that's not constant is on the other side. So if nothing is constant, then you would just solve for the only constant in this equation then would be R. So you would say PV over NT is equal to R. Or if, let's say, the pressure was constant, but everything else wasn't constant, then you would say that, so V over NT is equal to R over P. And the reason why you do this is because what you're going to say is that if the pressure was constant, only the pressure was constant, then what this means is that going from state A to state B, V over NT is equal to some constant. What that means is that then that VA over NATA is equal to VB over NTTB. You see? But you can notice, though, that when doing this, the constant doesn't matter. Whatever the constant value is doesn't matter. We don't need to solve for the constant. So if it was the case that going from state A to state B, all the parameters changed, the pressure changed, the volume changed, the number of moles changed, and the temperature changed, then what you've got is PV over NT is equal to R. Well, that means that PAVA over NATA is equal to PBVB over NBTB. We don't need R, though. We don't need to know what R is to do this analysis, right? And now, what's interesting about this is we can see from this type of analysis how Boyle's law, Charles's law, and Avogadro's law are built into the ideal gas equation. Because, okay, if we've got a process going from state A to state B that to where N and T are constant, so then in that case, just this form as it is already has all the constants on one side. So P times V is a constant. So PA VA is equal to PB VB. That's Boyle's law. Or if going from state A to state B, N and P are constant, then you've got, so V over T is equal to NR over P. Again, because N and P are constant, so N times R divided by P is always a constant. Well, then there you go. VA over TA is equal to VB over TB. There's Charles's law. Avogadro's law, P and T are constant, so what you've got is V is equal to V over N is equal to RT over P, because R times T divided by P is always a constant. So VA over NA is equal to VB over NB. There's Avogadro's law. And so that's what they're talking about in this chart here from earlier. You've got Boyle's law with respect to the ideal gas law, the N times R times T is a constant because N and T are constant in the process. So N times R, which is always a constant, times T is constant. With Charles's law, since N and P are constant, then N times R divided by P is a constant. And here's the other form of Charles's law where N and V are constant. And then with Avogadro's law, the T and the P are constant. Okay, so you can see how, again, there's two ways you can apply the ideal gas equation. One is comparing states, two separate snapshots of a gas, or the other would be you're just analyzing one snapshot of a gas, and you've got some of the information, but you're trying to solve for, like you might have P, V, and N, but you're trying to solve for T. Or you might have T, N, and P, but you're trying to solve for V. But to use the ideal gas law that way, in that case, we're going to need R. So how can we solve for R? Well, okay, in this next paragraph, it just starts to talk about what the meaning of ideality is. We'll come back to that later in a future video. But okay, before we can apply the ideal gas equation to a real system, we must evaluate the gas constant R. At 0 degrees Celsius and 1 atmospheric pressure, many real gases behave like an ideal gas. Experiments show that under these conditions, 1 mole of an ideal gas occupies 22.414 liters, which is somewhat greater than the volume of a basketball, as shown above. The conditions 0 degrees Celsius and 1 atmosphere are called standard temperature and pressure, often abbreviated STP. All right, so to find R, all you need to do is take some gas that you can assume is adequately far removed from the point of condensing, which, like it says here, many real gases behave like an ideal gas. By real gases, they're referring to any substance that exists as a gas at normal atmospheric conditions, so nitrogen gas, oxygen gas, hydrogen gas, etc., noble gases. So you take a real gas, and for any state of that gas, it doesn't matter what the state is, for a snapshot of the gas in time, you need to determine what the volume, temperature, pressure, and number of gas particles is. If you can do that, then you can solve for R with the ideal gas law, right? But like, you can think about how, again, because PV is equal to nRT is the ideal gas law for all circumstances whatsoever, then what gas you use to determine R or what state of that gas you choose also makes no difference whatsoever. Okay, so they don't go into details here on for when R was originally determined, what gas was used and what was the exact state, or the PVT and N of the gas. But we can think about how the most difficult parameter to determine precisely is N, and a precise determination of N is centered around the work of Avogadro, which, again, we're not going to go into details on how Avogadro's law and Avogadro's number were determined in this video. But so we can think about how a specific type of gas is going to be chosen for the determination of R that would allow for the most precise determination of N. Okay, now for the pressure, a pressure of 1 atmosphere is going to be used, right? A pressure of 1 atmosphere is the universal standard reference point for pressure in science. Okay, now for the example it gives here, it says that a temperature of 0 degrees Celsius is used, and then it goes on to say that the conditions of 0 degrees Celsius and 1 atmosphere are called standard temperature and pressure, or STP. But now this is different from at the beginning of the chapter when the textbook referenced what it called normal atmospheric conditions of 25 degrees Celsius and 1 atmosphere, so like a room temperature and 1 atmosphere. But these normal conditions weren't bolded and they weren't labeled as a standard reference. Okay, so this is still a little bit confusing. I'm going to go into a lot more detail on reference environmental conditions in the units and measurement playlist. So going forward in this course, here's what you need to know. So the IUPAC, the International Union of Pure and Applied Chemistry, defines standard temperature and pressure, or STP, relative to a pressure of 1 atmosphere and 0 degrees Celsius. Okay. Now, note that, however, since 1982, the IUPAC actually uses a standard reference pressure of 1 bar instead of 1 atmosphere, with the bar just being a close equivalent to the atmosphere, but it's just more of a convenient metric unit. So 1 bar is equal to 0.986923 atmospheres. So the bar and atmosphere are effectively the same. But the main difference, though, is that 1 bar is defined to be exactly 100,000 pascals, or 100,000 newtons per square meter. So again, the bar was just defined to be a pressure that was as close to equivalent as a 1 atmosphere of pressure as possible, to where it's more conducive to the metric system in that it's that perfect power of 10. Okay, so that's standard temperature and pressure as defined by a chemistry organization, the International Union of Pure and Applied Chemistry. Now, there's also the National Institute of Standards and Technology, which is another commonly referenced, commonly used standard, the NIST, and they define what they call normal temperature and pressure, or NTP, as a pressure of either 1 atmosphere or 1 bar, and a temperature of 20 degrees Celsius, or a temperature more near room temperature. Okay, and so that's all you need to know going forward in this playlist. Throughout the course, we'll periodically talk about standard reference conditions more, but in the units and measurement playlist, I go into a lot more detail on all of this. All right, so back to the determination of R. In this example, they're going to use some gas that is most conducive to precisely determining N, and the plan is that N is going to be equal to 1 mole. They're going to have 1 mole of this gas, and then the pressure and temperature of the gas are going to be at STP, so 1 atmosphere and 0 degrees Celsius. And then the volume is going to follow suit. If you fix the number of moles and the temperature and the pressure, well, then you can't dial in the volume. The volume is going to take on whatever it's going to take on. So you can think about how for an experiment like this, the volume chamber could be adjusted. So with 1 mole of gas in the chamber, the volume would need to be being slightly adjusted to allow for the temperature and pressure to be dialed in at 1 atmosphere and 0 degrees Celsius. Right? You're trying to dial in that 1 atmosphere and 0 Celsius, but it's not working. So you adjust the volume a little bit, and you hone in on that pressure and temperature. And at some point, you would finally be able to get both the temperature and pressure of the gas to 1 atmosphere and 0 Celsius. And at this point, the volume would settle into a certain position as well. And so, okay, it says here that at STP, experiments show that under these conditions, 1 mole of an ideal gas occupies 22.414 liters, which is somewhat greater than the volume of a basketball. So yeah, if we come here, gives you a visual of 22.4 liters. Okay, but now if we come back here, and note how it says that at these conditions at STP, 1 mole of, it just says an ideal gas, a general gas, occupies this volume. So that the type of gas doesn't matter. For any gas that follows the ideal gas equation, if there's 1 mole of the gas and the pressure and temperature of the gas are at 1 atmosphere and 0 Celsius, then the volume must be this 22.414 liters. And so now you have all the information you need to solve for R. You have a pressure, a volume, the number of moles, and the temperature. And so here's the universal gas constant in units of liter atmospheres per Kelvin mole. So yeah, you can have different R values depending on the units, right? No matter what, you're going to have to use an absolute temperature. So this is going to be either Kelvin or Rankine. N is always going to be in moles, but pressure and volume in general can be whatever you want, just some acceptable unit of pressure, so a force per unit area, and an acceptable unit of volume, a length cubed. And so there you go. Now we can apply the ideal gas law in reference to just a single snapshot in time of a gas. All right, one moment in time, take a picture. At that moment, that the gas is going to have a pressure, a volume, a number of moles, and a temperature. And with R, you just make sure that you're clear on what the units of R are that you're using, and that the pressure, volume, and the temperature and the count of particles match up with the units, and you can solve for whatever you need to solve for that single snapshot. Okay, so now next it goes on to talk about the combined gas law, but we've already gone over this, so it's just they're talking about the other perspective that you can apply the ideal gas law. So when you're comparing states of a given gas, a given type of gas, it's at state 1, then state 2, then state 3. That's when you rearrange the ideal gas law and put everything that's constant going from one state to another on one side and everything that's not constant on the other side, and then use this one over this one is equal to this 2 over this 2, this 2. In the most general case, you have all of the parameters are not constant, so you're just solving for R, and you get as general as it gets. You have P1 V1 over N1 T1 is equal to P2 V2 over N2 T2. Everything is changing, going from state 1 to state 2. But you can see how, in this case, you don't need to know what R is. You only need to know what R is for the case of analyzing just a single moment in time. Or here, you'll see the combined gas law as shown here, because in a lot of cases, you're dealing with a gas sample, a single gas sample in which the number of moles of gas isn't changing. So in that case, you've got the N mixed in with the R as a constant, and you're left with just this, right? Because you have PV is equal to nRT. So if N times R is a constant, then PV over T is equal to nR. So PV over T is constant. So there you go. P1 V1 over T1 is equal to P2 V2 over T2. Okay, now it says, so density calculations, it says if we rearrange the ideal gas equation, we can calculate the density of a gas. So if you got PV is equal to nRT, then we can think about, well, N over V, right? So a density is you've got an amount of substance divided by a volume. We typically think of density as like a mass per volume, like kilograms per cubic meter, but it's really, in a broader sense, density is just any unit that's in amount, like moles, right, then per volume. So in moles per volume, you've got N over V is equal to P over RT. So now we also know that the number of moles of any substance is not just a gas, but we're with the ideal gas law, we're talking about a gas. But if you want to determine the number of moles of a substance, then you can use the molar mass, right? So the molar mass is grams per mole, right? You just go to the periodic table and you get the whatever the formula weight is, or the molecular weight, or just the atomic weight, and numerically the total weight of a molecule or the chemical formula of any substance is numerically is the same thing as the molar mass, right? Which is the grams per mole. But now when you divide the molar mass by the mass of the substance, which you weigh like on a scale, then what you end up with is the number of moles, right? Because you have grams, and then that's the way we use molar mass. That's how we use molar mass to get the number of moles of molecules or atoms in a substance. So we're thinking about a gas, though, here. So thinking about a gas, the number of moles of the gas is the mass divided by, like the mass in grams divided by the molar mass. And so mass in grams divided by molar mass. I mean, you could put molar mass. It doesn't have to be in grams per mole. You could put molar mass in whatever units you want. But like if you're taking the numbers from the periodic table, then it's in grams per mole. So, okay, what they do is they say that, well, let's substitute for N in the ideal gas law. Let's substitute this M over lowercase m over capital M. And you just get another form of the ideal gas law to where, so M over V, the mass in grams over volume, that's the more traditional density we think about. They're going to say that this is equal to D, but you'll commonly see this written with a rho, right? So they substitute M over V for D, and now you've got the ideal gas law in terms of another form in terms of density, traditional density, with grams per volume, grams per liter, grams per cubic meter, whatever. So you've got M or D is equal to, with you have molar mass here. So let's see, you've got, I'll use rho. So rho is equal to P. So you can do P molar mass is equal to rho RT. There's another form. Again, this is applicable if you're dealing with a gas that's sufficiently removed from the point of condensing. It has a sufficient degree of ideality, then you can use this equation to model the gas or to find information about the gas. Okay, so unlike molecules in condensed matter, that is in liquids and solids, gaseous molecules are separated by distances that are large compared with their size. Consequently, the density of gases is very low under atmospheric conditions. For this reason, gas densities are usually expressed in grams per liter rather than grams per milliliter. Yeah, so you'll typically choose units, at least once you're done with the calculation and you've got your final answer, you'll typically choose units that are going to result in the magnitude of the quantity being something that, is not too big or not too small, something you don't have to use scientific notation for. Something like from like negative 100 to positive 100, right? And so what they're saying is that, just keep in mind, gases are going to be significantly less dense than solids or liquids. So you'll typically see different units used for the density of gases. Like you'll instead of grams per milliliter, you might see grams per liter. Okay, now it says, from what we have seen so far, you may have the impression that the molar mass of a substance is found by examining its formula and summing the molar masses of its component atoms. However, this procedure works only if the actual formula of the substance is known. In practice, chemists often deal with substances of unknown or only partially defined composition. If the unknown substance is gaseous, its molar mass can nevertheless be found thanks to the ideal gas equation. All that is needed is an experimentally determined density value or mass and volume data for the gas at a known temperature and pressure. Then, by solving for molar mass here, you can just plug in the density. You have the universal gas constant, whatever the temperature and the pressure are, to determine the molar mass. So what they're saying is that, yes, if you know the exact chemical formula of a substance, well, then you can get the molar mass just by using the periodic table and summing the atomic weights, the molar masses of all of the atoms in the chemical formula. But it's saying how this procedure only works if you know the actual chemical formula of the substance. But in practice, chemists are often dealing with substances of unknown or only partially defined composition. And so what you can do is, if the unknown substance is a gas substance, you can take advantage of the ideal gas law, because you can get the gas at a certain temperature and pressure and measure that temperature and pressure. You know the universal gas constant. Now, but you also need the density. So how do you get the density? It says that, so all that is needed is an experimentally determined density value or mass and volume data for the gas at a known temperature and pressure. So in a typical experiment, a bulb of known volume is filled with the gaseous substance under study. So you're going to know the volume, the temperature and pressure of the gas are recorded, and the total mass of the bulb plus gas sample is determined. The bulb is then evacuated and weighed again. So again, you can have a precise scale, a highly precise scale, and you just find what the scale is outputting when the bulb is filled with gas and when it's not filled with gas. Take the difference between those two and you get the mass of gas. And with the volume of the bulb, you just divide that mass by the volume to get the density. So you can imagine with really precise instruments, if you've got a really precise pressure and temperature and density, you can get a really precise molar mass, which is extremely useful information about some unknown substance, if you're trying to identify what that substance is. Okay, but now it says that the mass spectrometer has become the dominant instrument for determining molar mass, but the determination of molar mass by the density method is still useful.